In this video we want to talk about elasticity of demand. Now this is quite a big topic in economics, and it's one that needs careful attention. Essentially we're talking here about the responsiveness of markets to changes in, let's say, in the price of the product, or in the income of the consumers, or in their tastes or advertising expenditure, or in some factor, some determining factor of demand, such as the price of the product, the price of alternative goods, income, tastes, advertising expenditure, and perhaps others. But what we're looking to try to explain is the extent to which markets adjust when, let's say, the price of the product changes. Let's just concentrate on price. So if the price of the product is reduced, we'd expect more to be sold. But the question is, how much more? A small amount or a large amount? And this takes us into the area or the province of elasticity. Elasticity is the extent to which demand stretches or varies when the price changes. But bearing in mind, of course, it could be a change in income that brings this about, or a change in the price of other goods, related goods. So it can come about in various ways, but just to make it easy, in this introductory class we'll talk about the price of the product. The concept of elasticity goes back to Alfred Marshall in 1890 in the Principles of Economics. But it's a very important topic in economics and gets a lot of discussion within economics. Let's see what's meant by it, and we're going to keep this class as straightforward as we can. So quite a simple, straightforward presentation. Here we've got two demand curves. You'll see on the vertical axis I've got the price per unit. We have to specify the unit, otherwise it doesn't make sense. So we have to say the price per gallon, or the price per litre, or the price per ton, or the price per gram, or we have to specify some unit to make it sensible. And on the horizontal axis we've got the quantity and a little t at the end. It's the quantity per unit of time. It's the quantity demanded per unit of time, the quantity demanded per week, or per day, or per month. When we see t, time period, appearing in a diagram, it means we have a flow concept. There are two types of concepts here we need to distinguish. One is flow and one is stock. A stock concept does not change over time. So the stock of capital in the country. So it's the stock. Imagine if we could take a picture of the country, take a picture on a camera of the country. That would show the stock of capital at that moment in time. A flow concept are changes in the stock. So flow is a change in the stock. So in the example with capital I've just given you, then if we take the same picture next week, we would see the picture would be slightly different. The difference is the amount of investment and disinvestment in the economy. So investment is a flow concept. It moves over time. Stock, the stock of capital, let's say, the stock of goods in a warehouse, the stock means it's not changing. So when we talk about the demand here on our diagram just in front of us, we have it as a flow concept. Demand is a flow. It changes over time. So I'd say that my demand for petrol is 20 litres a week. But I have to say per week. If I said it was 20 litres, it wouldn't make any sense. Is it 20 litres a year, 20 litres a day? It makes a lot of difference. So we have to specify a time period. Now on the diagram we've got two demand curves here. Demand curve 1 and 2. You'll see that demand curve 2 is steep. It's steeper than the first one. The first one is flatter. It's less steep. Now these two curves represent the same product, let's say. Well, if those two curves did represent the same product, we have to ask which curve is the more sensitive to price changes. Now clearly it looks like the curve on the left hand side is more sensitive, because if the price drops by some small amount, the quantity demanded will vary significantly. On the diagram on the right side, if the price drops by the same amount, the demand will not vary a lot. So it looks like the demand curve 1 is more sensitive to price changes than demand curve 2. However, what if they're different products? One is soft drinks and the other is petrol. One is soft drinks and the other is butter or bread or rice or whatever. Now, which one is more sensitive to price changes? Well, we've got two different goods now, so it's very difficult to make direct comparisons. So we've got a problem when we look at a demand curve, and if we realize that demand curves for different products are different, it's difficult to get comparability because we're talking about different products. So if the price drops by the same amount, let's say from P1 to P2, you can see the demand curve on the left. The quantity demanded increases from Q1 to Q2, and that's greater than on the demand curve 2 on the right hand side. The quantity demanded is less, Q1, Q2. It's smaller than the quantity on the left hand side. So it does look like the demand curve on the left is more sensitive. It's more elastic. It responds more to a change in price. However, the curves actually could be the same. One could be in kilograms, or in grams, or in pounds and ounces, or whatever. The other one could be in tons. So the units in which we measure the output have to be the same. So we can't just look at a demand curve and say this demand curve is elastic or more elastic than the other demand curve. And we'll see there are lots of other technical reasons why we can't say that as well later in the video and in other videos related. But for the moment, you can see that the units in which we measure the output is critically important. So one could be kilograms, the other could be grams, the other could be in ounces, in the imperial measure. It varies. It could also be the case the two products are completely different, and one's measured in kilograms and the other's measured in litres. One is a solid and the other's a liquid. Totally different products. So looking at the demand curve does not indicate the elasticity of demand. We measure elasticity by eta. It looks like an N, as I said here, but the second part of the N, the leg on the second part, is longer than the first. It's the Greek letter eta, E for elasticity. So this is the symbol we use for elasticity. And we measure elasticity by this formula. We say that elasticity eta is equal to the percentage change in quantity, and I put change in quantity in a single quotation mark here. So it's the percentage change in quantity divided by the percentage change in price. That's all it is. It's the percentage change in quantity divided by the percentage change in price. And we write this on the right hand side here as the percentage and a little triangle. That means delta, more Greek letters. Delta stands for the change in. So it's, if we read it, it's percentage delta Q divided by percentage delta P. If we want to interpret the delta, as we should do, we'd say it's percentage change in quantity divided by the percentage change in price, because the delta just stands for change in. And we use this in mathematics when we can have a discrete difference in a variable. We call it delta. We can measure the difference. We can measure the change. That's known as delta. If we can measure it, it's delta. So that's how we measure elasticity of demand, using this formula. We work out the percentage change in the quantity divided by the percentage change in price. Unfortunately, again, it's not that simple. Let's move on. Here's our formula. Go back to it. If you look at the formula on the right hand side, and there it is again. Now, delta here means change in. That's what I just said to you. So remember that the little triangle is the Greek letter delta. Delta is the change in. In the formula, the triangle, if you like, the little delta means change in. It's the Greek letter delta. So that's all we need to know about the formula. It's not complicated. It looks quite mathematical, but it's not actually complicated. It's elasticity of demand is equal to the percentage change in quantity divided by the percentage change in price. And we represent the change in as a delta, a little triangle. Now, the price elasticity is measured by this, so we've already seen that. Elasticity is equal to the percentage change in quantity divided by the percentage change in price. It's worth noting. Now let's consider an example. Let's say that the price of a good increases by 2%, and as a consequence its demand falls by 10%. Now we want to work out how elastic is that good. We need to be able to compare the elasticities of goods. We'll see why we need to do this as we work our way through economics and through these classes. So for the moment we just want to do it. We just want to find out how elastic it is, or how inelastic it is. So we're given this data. Let's say that the price of a good increases by 2%, and as a consequence its demand falls by 10%. So let's just deal with that. Now substitute that into our formula. So go back to the demand falls by 10%, minus 10%, and the price of the good increases by 2%, plus 2%. So demand falls by 10%, price increases by 2%, plus 2%, minus 10%. Now insert it into the formula, and here we have the page we had earlier. So it's minus 10% over 2%, which is equal to minus 5. And that's how elasticity is worked out. It's just a number. There are no units associated with it. It's not 5 kilograms or 5 liters or 5 liters a week, or it's just a number. It's just minus 5. Because one percentage divided by another percentage is just a number. So we can see that the answer is minus 5. In fact, the answer is always negative for downward sloping demand curves. We always get it as minus. It's always minus something, because demand curves are downward sloping. So we usually just ignore the minus. We just say it's whatever, minus 5 or 5, it doesn't matter. So we say the answer is 5. Demand curves are, generally speaking, always downward sloping, so we say it's always going to be negative, so we can ignore the minus sign. So we know how to measure elasticity. Now instead of writing the percentage change in quantity divided by the percentage change in price, let's write out the percentages fully. Let's write out how to work out a percentage fully. How we would work out a percentage, of course, is we take the change in quantity divided by the quantity multiplied by 100 divided by the change in price divided by the price multiplied by 100. Like that. So if you look at the numerator, I'll just put the cursor onto the screen. If you look at the numerator up here, percentage change in quantity, well, there you have it. It's the change in quantity divided by the quantity multiplied by 100, which gives us the percentage. That's all how you work out a percentage. Very straightforward. And for the change in price, the percentage change in price here, we've got it here. Now, both these expressions are the same. The top one and the bottom one. Eta is the same in both. It's just a different way of writing it. The formula on the bottom is more worked out. It's more explicit. Of course, the hundreds in the numerator, this 100 up here and this one down here, they can be cancelled out. We can get rid of those two. So there they are, cancelled. Now we have one fraction divided by another fraction. We have delta Q divided by Q, that's a fraction, divided by delta P over P, that's a fraction. So we have one fraction divided by another fraction. Now we can tidy this up and see what we've got. Well, that's what we've got. We've got rid of the hundreds, so we have one fraction divided by another. Now, when we divide one fraction by another fraction, we say that we invert the divisor and multiply. That's what we're taught at school. That's the rule. Invert the divisor and multiply. Now, if we look at the, put the cursor back on, this is the divisor down here. We invert this one and multiply. Just turn it upside down and multiply. And it gets rid of this big division we've got here. Putting it another way, we turn the fraction on the bottom upside down and multiply the two fractions. Now, when we do that, it'll look like this. So we've taken the top fraction here, that's it there, and we've turned this one upside down and multiplied it. That's how you divide by fractions. Simple. That's what we do at school. Now just gather the terms, make it look a bit neater. So we can say this term here is the same as this one over here. We've just taken the delta P across under the delta Q and the Q under the P. So there we've got it. Now, our formula now states the elasticity is found by dividing the change in quantity by the change in price, and then multiplying this figure by the price divided by the quantity. It sounds complicated, but in fact we've only altered the appearance of our original formula. It's still the same formula, it's just we've played around with the arithmetic. So that's our original formula, and we've just moved it around and we found this bottom formula. Delta Q, change in Q, divided by the change in price, multiplied by the price, divided by the quantity. This formula is the one we use in practice to calculate elasticity. It's known as arc elasticity, arc, because we take small changes in price and a small change in quantity. These changes may be measured, and this gives us the idea of measuring across an arc. We're taking a small change in the price. So we move from one price to another price, very close to it. And then we look at the change in quantity. And because we're moving from one price to one very close to it, it's like moving across an arc. So it's a small change, but it's measurable, so it's called an arc. This is called arc elasticity because the changes are measurable. If the changes were very small, we'd have to use what's known as the calculus, which means we can't measure the changes. They're infinitesimally small. Now, elasticity along a straight line demand curve. Well, this often crops up. If we look at this straight line demand curve, here we've got a change in price divided by a change in quantity. And that's equal to a constant. The slope of the curve is a straight line, so the slope of this curve is constant. The slope is the same right throughout the line. which means that delta P divided by delta Q is a constant. And of course, therefore, its reciprocal, delta Q divided by delta P, is also a constant. So that's a constant and that's a constant. So constants all the way along, it's the same. Now here's our formula. So we know that delta Q divided by delta P is a constant. So we can just write it as K. K for constant. And if that's a constant, that means that the elasticity is proportional to the price-quantity ratio. So elasticity depends on the price-quantity ratio. Well, I suppose the first question is, how does that help us? Well, a lot. Because if we look at this diagram, let's take the point here where the demand curve touches the price axis, touches the vertical axis. At this point, Q is equal to 0. Well, that means Q here is equal to 0, so it means elasticity tends to infinity. We're dividing by 0, so elasticity tends to infinity. So at this point here, right at the axis, elasticity is infinite. And down here, P is equal to 0. So if P is equal to 0, here's P equal to 0. That means elasticity is equal to 0. So elasticity is 0 at this point and infinite up here. And it varies all along the curve. So we can't look at a demand curve and talk about its elasticity because it varies from 0 to infinity. So looking at the slope of the curve does not tell us the elasticity of demand. What we'd have to do is we'd have to think about the segment of the curve. You see, if we look at it, this section up here is greater than 1. So 1 is halfway along, and there is a proof for that, which I will produce later on in a separate piece of work. And down here, it's inelastic. So elasticity is termed as inelastic if it's less than 1. If it's greater than 1, it's elastic. So it's elastic up here. Sorry, I've just lost. So it's elastic up here and inelastic down here. And in the center, it's equal to 1. Now, you're probably thinking, well, so what? Well, all of this does have a big impact on revenue, for example, that for a company varying its prices to try and generate more revenue, when the elasticity is equal to 1, revenue is maximized. So there are relationships that we need to be aware of in the context of elasticity. But certainly, looking at a demand curve, we can't talk about its elasticity. We can talk about the elastic section, which is the top half. We can talk about the inelastic section, the section which is less than 1 but is equal to 0 or greater. That's the inelastic section. The elastic section is greater than 1 up to infinity. So we can talk about the elastic and inelastic sections. We can't talk about the curve itself, the whole curve, and talk about it being elastic or inelastic, because it varies all along the curve. It's also the case that the position of the curve influences the elasticity of demand. If you look at this one here, this diagram, here we've got two demand curves, D1 and D2. Two red curves. We've kept the gradients the same, so they're the same gradient. Now if we take the price of P1, we get a quantity of Q1 and a quantity of Q2. Well, look at the elasticity for Q1. Well, elasticity 1, eta 1, put the cursor back on, eta 1, this formula up here, eta 1 is equal to K times the price quantity ratio, P1 over Q1. So it's the elasticity here is P1 over Q1 times K. We can just say K is a constant. And over here, the elasticity is P1 over Q2. 2 is not very clear, but it's P1 over Q2. So it's P1 over Q2. Well, P1 is the same for both, but you can see that Q2 is greater than Q1. So over here, the denominator is greater, so the value of the elasticity is less. So the further out the demand curve is from the origin, the smaller is the elasticity. The closer it is to the origin, the greater the elasticity. So the position of the curve is also important. That's something else to be borne in mind. So now we know quite a bit about the demand curve. We know that the elasticity varies all along it. The sensitivity of demand varies all along the demand curve. So really we should be talking about the elastic section and the inelastic section. But we should also think about the location of the curve, if it's further out or closer in to the origin. Here's a demand curve. Now, here's our formula we had earlier, so very straightforward. And here we've got a fall in price from P1 to P2, leading to an expansion of demand from Q1 to Q2. It's cheaper, so the customers buy more. And this is our elasticity formula. We want to work out the elasticity of demand here. So it looks a straightforward exercise, given what we've been up to, except there are problems. We can work out the change in quantity. It's just Q2 minus Q1. The change in price is just P2 minus P1. So we've got that there and down here. So we have the change in quantity, Q2 minus Q1, change in price, P2 minus P1, times price over quantity. But which price and quantity? We got P1 as one price, Q1, or do we have P2 and Q2? Make a big difference. So we need to know which price are we going to take. Now if you read the textbooks on this, textbooks tend to say take the original price, which may sound reasonable. However, if you took the other price, you get a different figure. So this formula will give us two answers, depending on which price we pick, P1 or P2. If we pick P1, we must take Q1. If we pick P2, we must take Q2. So which one do we pick? It's a difficult one to deal with. In fact, we get two answers. We should calculate two answers. So when we calculate elasticity of demand, we should really calculate two answers, one for each. If the price difference is very small, we would get one answer. So if the price difference was very, very small, if delta P was very small, then really the two answers would be very similar. You could just calculate one of them and pick one of the answers. So ideally, delta P, and hence delta Q, should be very small. If it's very small, then we would get one answer. We could use what's known as the Stiegler approximation, named after a famous American economist, George Stiegler. And Stiegler simply proposed taking an average price and quantity. So take an average of P1 and P2, and take an average quantity of Q2 and Q1, and this will give us a single elasticity figure. So you were just taking an average. And that's sometimes known as the Stiegler approximation. So in this video we've looked at an introduction to elasticity of demand. We've looked at some complications with elasticity of demand, and we've got to follow this up with other videos on this topic because it's an important topic, as I said, in the context of economic analysis. It's also a topic that the general business population and community should be aware of. It's not the exclusive area for economists. It's not something that just economists should consider. It has got practical implications, and the more we get involved with this type of calculation and looking at the importance of the sensitivity of demand to changes, let's say, in the price of the product, the more we'll realize that this has got significant practical significance in business as well. But that's all we're going to deal with in this session, so let's leave it at that and say thank you for watching.